This is problem 14 from chapter 19, and this is the final example problem for this course. The rod of length L and mass M lies on a smooth horizontal surface and is subjected to a force P at its end, A, as shown. Determine the location, D, that's shown here, of the point about which the rod begins to turn. This is the point that has zero velocity, otherwise known as the instantaneous center of zero velocity. Okay, so we have three equations which we can use here from our equation sheet. So we have this equation here, which we can use for the x components and for the y components. So I was counting that as two equations. So because the rod is initially at rest, the initial velocity is 0. So for the x components, it's 0. For the y components, it's also 0. Plus, so coming out of the page, that would be the z direction. We're not going to be looking in the z direction, so we can ignore the forces which are going into the page or coming out of the page. So we only have the force P here, which is going in the negative y direction. So for the x components, since there's no net force in the x direction, this would just be plus 0 is equal to the mass times the x component. This would be of the final velocity. So this equation just tells us that the velocity in the x direction is equal to 0. Okay, now using this equation here for the y components, we have this force acting downwards. So the net force in the y direction is negative P. Okay, so that gets rid of the sum of the forces in the y direction. Then we integrate with respect to t, so that's the left-hand side of our equation, is equal to the mass times the y component of the velocity of the mass center. Okay, so we're going to leave that just the way it is here, and then look at equation 1912. So because the rod was initially at rest, the initial angular velocity is equal to 0. Then I have plus the sum of the moments integrated with respect to t. I only have the one force P here since the length of the rod is L. For the net moment, I get P times L over 2. Then I integrate with respect to t. And this is equal to the moment of inertia about g. Okay, so we have a slender rod here, and we're summing up, or we're looking for the moment of inertia about the mass center. So it would be the center of the rod here, that's 1/12 ml squared. So this is equal to this, 1/12 ml squared times the angular velocity. Okay, and then the L over 2, I can pull that outside the integral and bring it over to the other side. So I have the integral of P with respect to T. Bringing this over to the other side would be 2 over L. So on this side I would have 2/12, which is 1/6. If I divide both sides by L, that's M times L times omega. Okay, now compare what you have here and what you have here. The only difference on the left-hand side is this negative sign that we have here. So that just means that the velocity that we have here, the y component of the velocity, is going in the negative direction and not the positive direction. So let me draw a picture here. So if this is the center of the rod, that's moving this way with a velocity of v gy, so that has a negative component. And then the angular velocity, because this is positive, would be like this. That's the positive direction. Okay, so I can relate these two here, and maybe I just want to say absolute value of VGY, since I know it's going in the negative direction. That's equal to this 1/6 ml times omega, and then our masses cancel out. Okay, remember that we are looking for the location of the instantaneous center of zero velocity. Oh, furthermore, because the x component of the velocity of the mass center is 0, let's just call this the velocity of the mass center. Okay, now we want to go back to where we first learned about the instantaneous center of zero velocity. And we had this equation here. The velocity of point B is equal to the angular velocity crossed with this vector here, which goes to point B from the instantaneous center of zero velocity. So I want to write this as the velocity of the mass center is equal to the angular velocity crossed with this vector r, which goes to the mass center from the instantaneous center of zero velocity. When I do the cross product here, since the rotation is this way, the angular velocity vector is pointing up out of the page. So I cross that with this vector here, and I have to get the resultant vector going downwards. So that would be this crossed with this gives me something going downwards. So this vector is pointing to the left. And if this vector is pointing to the left, then that means that's going to point G from the instantaneous center. That means the instantaneous center is over here. Then I go to point G from the instantaneous center, and then doing my cross product like this, all the directions work out. So this is my vector here. Okay, and then since I figured out the direction, I can now just look at the magnitude. Okay, but now compare this with what we have here. This is the magnitude of the velocity of the mass center, which is actually what this is here, since the x component is equal to 0. We have omega here and omega here, so by comparison, we have the magnitude of the vector here is, that takes care of omega, so this is just L over 6. The units work out correctly. So this vector has a length of L over 6, and the instantaneous center is to the right of point G. Okay, the rod had a length of L, so the distance from point A to point G is L over 2. And let's go back and see what it was we were supposed to find. So determine the location D. Okay, that's this here. So that's being measured from the left end of the rod. So that's L over 2 plus this distance here, which is L over 6. So D is equal to L over 2 plus L over 6, which is 2/3 times L. Okay, so that's the solution for problem 14. That concludes chapter 19, and it also concludes ENR 252. So thanks for tuning in. Congratulations on making it to the end, and good luck on your final exams.